A grey back idles beneath the swell, rising and falling with a patient metronome. One eye shuts against the glare. The other watches the surface, flanks slow. The blowhole remains just above reach, poised for the next measured breath. Beneath, a hemisphere of cortex cools into quiet while its twin stays on guard, steering, timing, tasting current. This is marine mammal sleep adaptation at ocean scale, where rest never severs control. In a world with no pillow and no shore in sight, the giant that never fully rests drifts like a living buoy, half of it at ease, half of it awake. Across pelagic deserts and cold, rich fronts, long-lived travelers nurse calves, migrate thousands of miles, and feed in pulses tied to plankton and fish. Air is life. Drowning is a sentence one mistake away. Rest must happen without sinking, without forgetting to breathe, and without losing track of companions. Calves draft in the slipstream of mothers, learning breath by breath. Groups sometimes log at the surface like driftwood. Others dip into quiet columns and rise again. Only after the pattern emerges does the name snap into place. These are whales and their kin, with a method that makes vigilance a form of sleep. Whale resting behavior looks deceptively simple. Slow drift, sparse breaths, a soft eye. But inside the skull, the division is exacting. Whale sleep. Half-brain. The giant that never fully rests is less a slogan than a blueprint. Here is the paradox stated plain. How did marine mammals evolve to divide sleep between brain hemispheres while maintaining complex functions? Breathing must stay under voluntary control. Surfacing must be timed. Calves must be guarded. Predators and vessels must be detected. Yet brain tissue demands sleep to restore synapses and clear metabolic waste. In dolphins, electrodes show unihemispheric slow-wave sleep with one eye open, then the sides swap after minutes or hours. Vigilance persists and swimming continues in gentle arcs. Fieldwork suggests large divers enter brief, repeated rest bouts, sometimes vertical, heads near the surface, before resuming travel or foraging. The contralateral eye, opposite the sleepy hemisphere, often remains open. In this framework, whale unihemispheric sleep and the broader cetacean sleep cycle break the usual rule that sleep arrives as a whole brain state. The solution is asymmetric. One side idles, the other keeps time, posture, and breath. Dolphin half-brain sleep demonstrates the principle in coastal waters. Offshore giants may express a slower, deeper version tuned to mass and buoyancy. It feels impossible to explain without a cost, yet the record shows lineages surviving for tens of millions of years on this divided rest. 3 hypotheses lead the debate. First, the respiratory imperative. As conscious breathers, these animals cannot surrender the timing of inspiration to a brainstem autopilot for long. Keeping one hemisphere awake preserves the motor patterns for surfacing and the awareness of air. Studies indicate that during whale unihemispheric sleep, breathing becomes slower but remains reliable, and posture stabilizes near neutral buoyancy. The trade-off is limited depth of rest. One side works while the other recovers, stretching the night into many small payments instead of one large one. Second, vigilance and social constraint. Predators, storms, and ships impose risk. An open eye and an alert hemisphere sustain watch, track podmates, and shepherd calves through low-speed travel. In mothers, evidence suggests reduced rest pressure until the young can maintain rhythm, a tweak in the cetacean sleep cycle that prioritizes care. Dolphin half-brain sleep aligns with paired swimming and acoustic monitoring, letting one side of the brain listen while the other sleeps. The cost is a ceiling on how deep sleep can go before awareness blinks out. Third, navigation, thermoregulation, and energy. Ocean layers differ in temperature and drift. Keeping partial control may hold body position in favorable strata and keep heat loss in check. Some researchers propose that asymmetrical neuromodulators bias one hemisphere toward wake, while the other accepts slow waves, a neural circuit solution that allows reversible lateralization without damage. Scientists still debate the exact wiring, whether reduced cross-hemispheric coupling enables independence, or if dynamic inhibition does the job on demand. What is clear is the outcome. Marine mammal sleep adaptation lets flesh and intellect share a watch bill. It has been quietly rewriting what we thought we knew about how brains must sleep. Mechanism meets behavior in the water itself. Buoyancy and lung volume set the float point. Exhalation before rest reduces sinking. Slow fin strokes or passive glides keep headings true. Logging at the surface grants easy breaths, but risks ship strike. Submerged drift hides the silhouette, but requires precise timing to breathe. Whale resting behavior shifts with sea state, light, and company, an elastic routine rather than a single script. The balance is brittle. Disruption by noise or traffic can shatter the schedule. Calves burn energy to keep up. Adults may trade rest for safety when conditions sour. Even then, the pattern returns because the need for sleep does not vanish. It only divides. The sea darkens, the surface smooths. A great body rises a hand's breadth, exhales, inhales, and settles again. Half the cortex sinks, half holds the world together. Can you truly rest while staying half awake? The answer floats in the quiet geometry of whale sleep half-brain, the giant that never fully rests, where a watchful hemisphere protects breath, calf, and course. Nobody knows why some individuals linger longer on one side, or how plastic this split becomes under stress. But the habit endures, an untraceable seam between wake and sleep. If the oceans grow louder or busier, that seam may fray. For now, the divided mind drifts on, and the mystery keeps its distance just below the next breath.